Hi, welcome to educator.com. Now let's talk about standard normal distributions and z-scores. So first we're going to contrast the normal distribution against this standard normal distribution. And it's going to be pretty easy because just by knowing the normal distribution, you already know the standard normal distribution. Then we're going to talk about some normal distribution problems and contrast that with standard normal distribution problems. All right, so before we talked about how the normal distribution really is a family of problems. It's not just one shape, but it could be sort of stretched or shrunk on that x-axis. And because of that, it's actually an infinite set of distributions all with different means and different standard deviations. So you could have means of 5 and standard deviation of 10. That's one normal distribution. And then another one could have a mean of 1 and a standard deviation of 2, right? So there's like an infinite number of these. They all fit the empirical rule, though. Now, because it's sort of problematic to work with like every single one of these different normal distributions, they've thought of this transformative system where you transform all normal distributions into what is called the standard normal distribution. And there, what we're doing is we're making the mean 0 and the standard deviation becomes 1. This way, we don't have to worry about the actual values, right? We don't have to worry that the mean is actually 50. We just have to know, oh, the mean is in the middle, right? And the standard deviation, by being 1, makes it just really easy for us to label this stuff, right? So in a standard normal distribution, what we've really done is we've transformed the values into z-scores, or what we call standard deviations, right? So we've normalized everything. We don't really care that the standard deviation is actually 10. We just care how many standard deviations away they are. So are you 1 standard deviation away, 2 standard deviations away? And because of that, we've changed this x-axis. Instead of actually putting the values, we're now putting the z-scores. So that's really the only difference between the normal distribution and the standard normal distribution. In the standard normal distribution, we basically ignore the values and we only use the z-scores. And we have everything in terms of standard deviation. Are you 1 standard deviation away, half a standard deviation away? That's all we really care about. So in a normal distribution, which I'll draw in blue, in a regular normal distribution, what we usually have is probability, which is the area. So this is represented by area. The raw score with the mean, median, and standard deviations and actual values, things like 550, 450, right? And we have the z-score. 0, -1, +1, right? So that's what we think of as a normal distribution, a regular normal distribution. What we do in the standard normal distribution is we basically ignore that part, right? So it's the same thing. We still have probabilities and we still have the z-scores, right? But now all our scores are z-scores. We don't have any other scores other than that. So that's really the only thing that's different about a standard normal distribution. All right, so now let's talk about the z-score, the raw score, the mean, and the standard deviation, and the relationship that they have to each other. Before, we really did it in a very sort of intuitive way. For instance, if our mean was 10, so our mean is 10, and our standard deviation is 5, right? How do we know where to draw these notches? Well, if it's a normal distribution, we know that approximately this area should be about 68%, more than half. What you could do is look for the point of inflection. Often in my drawings, the point of inflection is really hard to see, but in a nicer drawing, you could see the point of inflection. But what we could see is 1 standard deviation away means that it's a distance of 5, right? What would this value be right here? Well, since it's 5 on the negative side, all we have to do is subtract 5. And that's pretty intuitive, right? If we want to go another 5 steps to the left, that would be 0, right? And if we wanted to go yet another 5 steps to the left, that would be -5. And if we wanted to go yet another 5 steps to the left, that would be -10, right? And so on and so forth, right? Same thing on the positive side. If we wanted to go 5 steps to the right, that would be 15, 20, 25, 30, so on and so forth, right? On to infinity and negative infinity. Now, before we just did it in a very intuitive way, and these notches just correspond, we've drawn them so that they correspond with z-scores. This is 1 standard deviation out, 2 standard deviations out, 3 standard deviations out. But there is a systematic relationship that we could exploit here and turn into a formula between the z-score, the raw score, the mean, and the standard deviation. If we wanted to go 2 standard deviations out and find what this value was, in order to find it, in order to find the raw score, what we do is take the mean and then add the z-score multiplied by the standard deviation. And this actually works for on the negative side too, because when we have a z-score of -1, then you would subtract the standard deviation instead of adding to the mean. So this formula ends up being really good for us. Instead of raw score, we usually call the raw score the x's. And instead of writing out mean, we would write mu. And then we could keep z and write sigma as our standard deviation. So now we see a formula here that allows us to go from the mean, the z-score, and the standard deviation into a raw score. Now, we could use this formula to find anything, any of those 4 things now. If we wanted to find the z-score, for instance, and we did some algebra to this, we would just see that that's actually the distance between the raw score and the mean divided by the standard deviation. And let's think for a second about what that means. That means the z-score is take this distance and then cut it up into these chunks. How many of those chunks do you have, right? So the z-score really is telling you how many standard deviations are you away from the mean, right? So it's totally relative to the mean and standard deviation. Also, you could use this very same formula to solve for the mean and standard deviation, right? So we could do that over here, right? So let's say we wanted to solve for the mean. What would that look like? Well, all we would have to do is move this over. So that would be x minus the z-score multiplied by the standard deviation. And then let's say we wanted to find standard deviation. What would we do then? Well, that's pretty easy as well. All we have to do is you could just take this formula and swap these guys. And so that would be standard deviation equals x divided by z. Right? So here we see that using this very simple formula, and you could just remember one of these because having one of them, you could derive the other ones from it. Just by having one of these formulas, if you had any 3 of these, you could solve for the 4th one, right? And you don't even have to do the algebraic transformations. You could just plug them in and find what's missing. Yeah. All right. So far, we've only talked about z-scores where it's nice and even, like 1, -1, 2, -2, right? But we haven't talked about weird z-scores. For instance, what about a z-score of something like 0.5, right? What would be the area over here? Well, some of you may be tempted to take 34%, 0.34, and divide it in half. But as you'll see from this picture, that won't quite work. You're not really dividing this area in half, right? This area still ends up being slightly bigger because it's slightly taller than this area, and this area has this big chunk cut out of it, right? So, so you can't just divide it by half. That's not going to be a good strategy, right? That's not going to give you the right area. So how do we deal with this? Well, there's two ways of dealing with these weird z-scores and how to go from these weird z-scores to probabilities that we don't know yet, right? That are not nice and even, like 34, 13 and a half, you know. Okay, so there's two ways of doing it. One way is by looking it up in a table. Often there are tables in the back of your textbook or even in the back of an AP statistics like Princeton Review book or something that show you the transformations from weird z-scores like 0.5 and 0.67 and 1.9, right, to probabilities. So that's one way of doing it, using z-tables. Z-tables. The second way of doing it is by using Excel or your calculator. If you have a fancy TI something calculator, it should also come with similar functions to Excel. And so I'm going to show you those two methods of how to go from weird z-scores to probabilities at those z-scores and vice versa. How to go from the probabilities, like weird probabilities, like 50%, we don't know where, or like 51%, right? Like we don't know what this value would be for 51%. How to go from those weird probabilities into the weird z-scores. All right, so first let's talk about the method by using the tables in the back of your book. Usually it's the first table you see back there, table A or something like that. And let's break it down. A lot of tables look somewhat like this one. Yours might look slightly different, but probably roughly similar. What it shows you up here is exactly what probability is plotted down here. What it shows you is the probability that's shown sort of on the negative side. So everything below the z-score, right? So, and this is what we call the cumulative probability because you're accumulating it as we go right? So it's adding up all the probabilities on this side. So this is showing you the cumulative probability at the z-score. Now, the table entry for z is the probability lying below z. So here are the z-scores, and these are the probabilities. Now, for the weird z-scores, what would really be helpful is if we had z-scores for, we had the z-score of negative 0.34, negative 0.341, negative 3.42, negative 3.43, right? So we had all of these decimal places, right? So it would be really nice if we had all these different z-scores. But that would be a really, really skinny list, right? A skinny list of a whole bunch of z-scores, and then a skinny list of a whole bunch of different probabilities. Now, that would be a very, very inefficient use of space. So what a lot of tables do is they put the z-score up to, like here, it's up to the tens place on this side, and then they put the hundreds place on this sort of dimension, right? So in order to find the probability for the z-score negative 3.45, right? You have to find negative 3.4 and then go to 0.05. So it's sort of like you add this, you sort of stick that on there, right? If you added it, it technically wouldn't work because it's negative. But pretend this is negative 2. So here, that would be negative 3.45, right? And at negative 3.45, the cumulative probability is 0.05. 0.0003. Notice that it's a very, very small probability. It's not 0, but it's very, very small. So let's do another example. Let's say we wanted to know the probability at the z-score negative 2.48. So we'd go to negative 2.4 and then also go to 8, and that would be our probability, 0.0067, less than 0.01, right? Less than 1%. Now, what if we wanted to find out the upper side, right? Like we're like, oh, you're only giving me the cumulative probability on the lower side. What if we wanted to find out this probability at positive 2.48, right? What would we do then? Well, because the normal distribution and the standard normal distribution to boot is perfectly symmetrical, what we would see is that if we know it for the negative side, we could just flip it over on the positive side. So if the negative side over here at negative 2.48 is a probability of 0.0066, then this too is also 0.0066 because it's perfectly symmetrical. So you don't really need to have both the positive and negative sides. Oftentimes, tables might just give you the positive side or just the negative side. Sometimes they'll give you both, but you don't actually need both. You could just figure it out from there. All right. Now let's talk about how to do this on Excel. For Excel, there are nice functions that Excel has pre-written out for us so that we don't have to actually look it up on a table. For normal distributions, when you know the mean and the standard deviation, there's ways to go from the raw score to the area underneath the curve. So basically, it's very similar to that picture we saw on that z-score. What it'll give you is this cumulative probability, so the entire area below that value. And so the normal distribution, you need to enter in the mean and the standard deviation. So in order to go from the score into the probability, you would use the norm dist function. And you would put in the score, but you'd also put in the mean, the standard deviation, and there's another thing. You also have to put in true in order to get the cumulative probability, because this is sort of asking cumulative probability, and you're like, true, yes. And that will give you the probability at that score, the cumulative probability at that score. Norm inverse is just the inverse of that. So here you give it the probability and it spits back out the score. So here you give it the probability, the mean and the standard deviation, and it spits back out to you the score. So notice that these two are inverses. That's why one of them is called norm inv. Because in one you get the probability and the other you get the score, right? So these are our two flipping around values. For standard normal distributions, you don't need to enter in the mean and standard deviation because all standard normal distribution means are 0 and the standard deviation is 1. The mean is 0 and the standard deviation is 1. And so it makes it a lot simpler for us. The only difference between normal distribution and standard normal distribution is this one little letter. All you have to do is remember to enter in norm S dist. And here you could just put in the score, forget everything else, and it'll spit out the probability. For norms inv, it's exactly the opposite, where you put in the probability and it'll spit back out the score. And I should say z-score here. Now, another handy little function might be the function standardized. Here, you put in the raw score, the mean and the standard deviation, and it will give you the z-score. This standardized formula simply uses, this standardized function simply uses the formula that we talked about earlier, where in order to give you z-score, it takes the raw score, or x, minus mu, divided by standard deviation. All right, so given that, let's look at a few examples and do them in Excel. The distribution of SAT scores for math for incoming students to the university was approximately normal. So that's, again, important. It has to say approximately normal. Watch out for that. I don't know if you guys have tricky instructors or tests, but sometimes they might give you a problem that looks like a normal distribution problem, but it doesn't say it's normally distributed. With a mu of 550 and a standard deviation of 100, what percentage of scores were 400 or below? Now note that 400, if you transformed it into a z-score, wouldn't be a nice even z-score like -1 or -2. It's actually like -1.5, right? So that's going to be a little bit difficult for us to use just the empirical rule. That's why we're going to have to use something like either the table in the back of your book or Excel. So here I just have an empty Excel sheet. And one thing that I'm going to do is I'm just going to use my columns to denote probability, raw score, z-score, just because that's going to help me keep track, like, okay, what am I doing, right? And I'm also going to write down my mean and standard deviation just to help make things a little easier. 550, 100. And I need probability. And I need my probability where x is less than 400. So that's what I'm going for. My raw score is 400. And my z-score, what is my z-score? Now, I can just do this in my head, and so can you. It's just the distance, 150 divided by 100, so, and it's on the negative side, so it's -1.5. But just to practice using Excel, let's use our standardized function. So standardize. And Excel will guide you into what exactly you need. You need your x value, the raw score, the mean, and the standard deviation. And so I'm going to close my parentheses, and I get -1.5. The other way you could do this in Excel is actually do the formula, because you know that you need the raw score minus the mean, and all of that divided by the standard deviation. And I get the same thing, but I just wanted to illustrate for you. That's what the standardized function is doing. Once you have that, now you need the probability. I could find the probability in two ways. One, I could use the standardized, the standard normal distribution, or I could use the regular normal distribution. Let's do both. So first, I know that it's the norm dist. I don't need the inverse one because I have the raw score. I need the probability. So let's start with norm dist. And here I know I need my x value. And I know I need the mean and the standard deviation. And it's going to ask you cumulative. And you just write true. And it gives us 0.0668. And that sort of makes sense. If we think about where -1.5 is, it's between -2 and -1, right? If it was at -1, it would be like 16%. If it was all the way at -2, it would only be like 2%. So 6% sounds about right. It's in between 2% and 16%. We could also do this by using norms dist. So norms with the S, dist. And for that, all you need is the z-score. So I'm going to put in my z-score. And I should get the exact same thing, because remember, the z-score corresponds with the raw score, right? And they're right above each other. So the probabilities at that point should be exactly the same. All right. All right, now let's talk about the different types of problems. Now that you know z-score and standardized normal distribution, what kinds of problems might come your way? Well, now the full set of information, you don't always need all of these numbers, but the full set of information is the mean, the standard deviation, the probability, the raw score, or x, and the z-score, or I'll just usually write it as z, just to make it simpler. So that's the full set. Any one of these things can be missing, and you could find it, right? So what's missing here? Here we have that same prompt. It says what percentage of scores were 400 or below. So that's percentage of scores. Or it might ask what percentage of scores fall below the z-score, negative 1.5, right? My negative sign didn't go over. So here we see that they're both about percentage of scores. So what might be missing is this. If you have either one of these and these two, you could find it, no problem. Here's another set of problems. Same prompt, but what's missing here? Here it says what math score separates the lowest 10% from the rest, or what z-score separates the lowest 25% from the rest. Here you have the probabilities and you have the mean and standard deviation, but one of these two things might be missing. So I think of these as the score missing problems. So we have probability missing problems and we have score missing problems. Now the last set looks like this. Note that this prompt does not give you the standard deviation, but it does give you the z-score and the raw score so that you could find the standard deviation here. Or it gives you the percentage and the raw score, and then you find standard deviation, right? So here, something like the standard deviation is missing. You could also find the mean to be missing as well, and they would look very similar to these problems. As long as you have some combination of the other variables in place, the other values in place, you could actually figure out what's missing. So now let's edit our shape analogy that we did in the previous lesson. I'm going to skip over a lot of this because it all stays the same. The only part I want to draw your attention to is right here. Before, we could only look at probabilities and raw scores, but now we have expanded our repertoire. We could look at probabilities to raw scores to z-scores and even find the missing mean and standard deviation. And that is all done through a combination of the z-score formula as well as either the tables or Excel. Now let's do some problems. Here's example 1. In the US, the distribution of deaths due to heart disease, 289 deaths per 100,000, standard deviation of 54, and cancer, a mean of 200, standard deviation of 31, are roughly normal. That's very important. Okay, so we know that we could use our normal distribution stuff. In California, 240 deaths are from heart disease, and 166 deaths are from cancer per 100,000 residents. Which rate is more extreme compared to the rest of the states, the average for the US? All right, so we have California's death rates from heart disease and its death rates from cancer. And we want to know, okay, which of these are really extreme? One way that we could find out is by finding out the z-scores. All right, so I'm going to get my Excel out. All right, so let's first start with the US. The US mean for heart disease, so I'll use this row for heart disease and this row for cancer. So the US mean is 289, And the standard deviation is 54. For Cancer, it's 231. We want to know how extreme the California deaths are. It's hard to compare with just the numbers because even though 240 deaths is less than 289 and 166 deaths is less than, certainly less than 200, we're wondering how much less? How far away from the mean are you? And one way we could do that is by using z-scores, because z-scores will give you the distance in terms of standard deviation. And because these two populations have very different standard deviations, that's worth knowing. And so here's California. Heart disease and cancer. And in California, the mean is 240 and 166. And what we might want to know is the z-score. So what is the z-score? So I might just put standardize and put in my x, put in the mean that I want to, the population mean, the theoretical mean I want to compare it to, and my standard deviation. Now, obviously, I could also do my x, subtract the mean, put that in parentheses, divide by standard deviation. All right, so here we see that the z-score for heart disease is about 1 standard deviation away, negative 0.9. Now, how far down is cancer? How much less is cancer? So how much more healthy are Californians in terms of cancer? And for here, I'll put in my sort of regular formula just so that we practice that too. So cancer, my cancer x minus the population, the theoretical population, divided by standard deviation, because I want it in terms of standard deviation steps. And we find out that cancer, and this is probably because the standard deviation is smaller, it actually is sort of out farther than heart disease. So the cancer rate is more extreme, and more extreme in a positive way. It's more extremely low than heart disease, although they're very close. So here, the trick is find rates in terms of standard deviations, or z-scores. All right, example 2. Heights of male college students in the US are approximately normal. Estimate the percentage of these males that are at least 6 feet tall. Now, it would help if we just sketch this out real briefly. So here's my mean of 70.1 and my standard deviation of 2.7. What percentage of these males are at least 6 feet tall? Now, what helps is if you transform the 6 feet into inches. So that's 72 inches, because these are in inches, because 70 feet is a little crazy. So where is 72 inches? So that might be something like this. What percentage of males that are at least 6 feet tall? So I want all of these people, because all of these people are at least 6 feet tall. They might be 7 feet tall, but they're at least 6 feet tall. So that's what I really want. So what might be helpful is, instead of my raw score, if I could find my z-score, and then I could look it up in the table in the book, or I could use Excel. I'm going to use Excel to help me. Let me move down. All right, so let's find the z-score for this. So in order to find z-score, Actually, let me write the formula here. So in order to find my z-score for 72 inches, that would be 72, which is my x, minus the mean, 70.1, all divided by standard deviation, 2.7, because I want the jumps. How many jumps away? My jumps are 2.7. Okay, so that's standard deviation. So now I'll pull out my Excel. All right, and I could just put in 72 minus 70.1, all divided by 2.7. And I find that my z-score is 0.70. And so in order to find the area, the cumulative area, and remember, cumulative area means this side. So Excel is going to give me this side. That's not what I want. I want this side. So I might put in 1 minus this area in order to get that area. So 1 minus. And then I'll just put in my norms, because I have my z-score, inv. And, oh, sorry, I want my probability, so I put in norms dist. Thankfully, Excel gives you a little hint, so if you're off, it's okay. And put in my z-score. And what I get is 0.24. So about 24% of males, of these males, are at least 6 feet tall. So this area is about 24%. So if I want to write it all out, I would write my probability where x is greater than 72 inches is 0.24. Here's example 3. In a standard normal distribution where p of z-score less than 0.41 is equal to 0.659, what is the mean and standard deviation? Actually, this is a trick question. Before you go off and try to find z-score and all this stuff, note that it says standard normal distribution. And in every standard normal distribution, the mean is 0 and standard deviation equals to 1. Ta-da! Example 4. Find the percentage of values in a standard normal distribution that fall between negative 1.46 and positive 1.46. So this would be nice if we sort of sketched it out so that we know what to expect. Here's 0. And since this is a standard normal distribution, that's how I know it's 0. Here's, maybe here's about 1. So here's maybe where 1.46 is, like a little less than half. Mine's probably a little bit too much less than half. Like here. All right. So I want to find this area right in between. Well, usually we look at, the area between -1 and 1, and we know that's 68%. So we know that it's a little more than 68%. It's not quite like maybe 95%. It's not quite that high, but it's somewhere in between 68 and 95%, right? And so let's try to figure this out. One way we could do it is by using our Excel or looking it up in our book. In our book and in Excel, the problem is that they will give you the cumulative distribution. So they will give you this area, right? But what we really want is this area. So what do we do? One thing we might want to do is just use our ability to reason. So this is 50% of that curve. If we take 50% and take away this area, so we could use norms dist and put in negative 1.46, then that should give us this area right here. So this whole area is this. This area is in blue, and that should give us the red area, okay? All right, so here I'm going to put in 50% minus norms dist negative 1.46. And then I want to take that area and multiply it by 2 because I want the other side too, and it's perfectly symmetrical, so I don't have to do any work. Just have to multiply by 2. And I get 0.8557, right? So a little bit close to like 86%, and that makes sense. It's more than 68%. It's less than 95%, right? So 86%. So my answer is where negative 1.46. My z falls in between this and this value is negative. Is 0.86. 0.86. All right. So that's example 4, and that's it for the standard normal distribution. Thanks for watching educator.com.